So we had started linear regression in the last class, and we'll hopefully finish multiple linear regression. It's just a simple extension. It's hot. It's hot, right? I was also feeling hot. There's at least one more person who's feeling hot. So the goal for today is to finish that some of the things that we left last time. इसी चले थोड़ा सा मतलब टेम्परेचर कम करें. हाँ. So one of the things that we have to always do whenever we are fitting a model is to, you can fit anything that you want in principle, but you'll always have to go back and see whether the model is indeed capturing the assumptions that you had initially began with, right? Like ideally in an ideal scenario you would test everything and then only you will run linear regression, but as you will see in some cases it might not be possible, because if you have one variable then fine, but if you have multiple variables, how do you diagnose it? So one approach, and not every pattern is something that you can always plot to begin with, but there are different scenarios of overall the kind of regression and the kind of residual components that you will see. For example, in this case, what is regression, right? So the regression is essentially trying to, the overall goal of any regression technique is to predict whether you can capture the average value of y given a particular value of x. So this regression is nothing but a measure of how different is your prediction from that mean value. That is your regression line. These are 4 different scenarios of what happens. So in this case, the residual is very small, so you're able to do the prediction pretty quick or pretty nicely overall, because the predicted value is close to the observed value. But if it is very distinct or very different from this mean line, so this is the large, that's why it results in large residual. There is no right or wrong here. These are the 4 different scenarios that can happen with any point, right? Like, so this same point, if you take on the other extreme, is it has small regression but it has a large residual, so you're not able to capture the point overall, but it is very close to the mean expression of the line. And all these 4 different possibilities exist in your data. This is just to show you that when you fit the data, then any of these 4 possibilities can hold true. But if you remember, or if you recall, we had started with a particular assumption about the data, which is that any linear model needs to be follow the models of linearity, right? What is L? Linear. There has to be a linear relationship that you're trying to fit. I, independent, right? So independence of what? What is independent? So if fitting a linear model, we had tried to make a mnemonic out of it by saying that it needs to satisfy or some of them, if not all of them. L is, there is linear relationship. I is independence of y. What does that mean? What is independent? Y should be independent of what was the independence assumption here? What is independent? Yeah, EI is residuals are independent. What is N? Yeah, so these are also normally distributed. What are the other stuff? Yes, correct. So equal variance, which is the sigma square is constant. It doesn't vary as a function of I. Okay. Anything else which we missed? These are the major ones that your assumptions will have to be satisfied. Based on these rules, you can think about actually how will you diagnose whether these conditions are holding true or not. So there are different criteria of how you can diagnose once you have done the linear regression, once you have fit the model. How can you actually diagnose whether it's a good or a bad fit? The first pattern that you can look into is what is happening to the residuals. As you remember, or as you recall right now, that the residuals are expected to not have a they should not be a function. They should be independent of what you fit. There should be no dependence on what particular value of yi am I picking. It should not happen that as my y increases, the residual increases, for example. These are supposed to be not related to the fit value. So the first plot that you can plot is you can plot the residuals against the fitted values. That should be a flat line, which means that there is minimal dependence of residuals on yi. It should be equally spread along these fitted values, and that will mean that it's hovers around that y equal to 0 axis, because residuals overall will sum up to 0, so they hover around that particular mean value. You can based on what you see here, you can actually figure out what the patterns is, and I'll show you in the code, for example, how can you simulate different scenarios. Here there is of course no pattern, so or somewhat less pattern. It will never be fully flat because there is some amount of information that will always get leaked into how you're fitting this value, but overall there should be relatively a flat line. The second assumption is about the residuals being normally distributed. So if you recall a couple of lectures, or maybe 3-4 lectures ago now, we had described this plot called the QQ plot, which is the quantile against the quantile plot. So the simplest test, if you want to test if two different distributions are, if a distribution follows normal or is normally distributed, is you can plot it against the theoretical quantiles. So if I have a distribution which looks like this, and I want to compare it to a standard normal, which is 0 and 1, what I can do is I can plot at what values do I have my quantiles. So if it is indeed a normal distribution, this one-to-one map of where is the quantile in my standard normal, which is your theoretical distribution, lies again, which is on what you plot on the x-axis, and on the y-axis you plot the standardized residuals, which is you estimated E of I, yi minus yi hat. You can standardize them. You have, by essentially doing the z-score stuff, which is you take any value, you subtract the mean, and you divide it by the standard deviation. This is expected to follow a standard normal distribution. What you're essentially doing is now you're looking at the quantiles of this and plotting them one against each other. If it is indeed normal, it will follow along on this horizontal, in this 45-degree line. The third is to look for scale versus location plot. This is a good test for testing whether residuals are evenly distributed across the range of predictor values that you had. So the first plot was against the fitted values. This one is more of a test for what happens overall if you look at the actual if you look at the overall distribution of these z-scored version of your residual. So that's why these are standardized residuals. So if you remember, or if you, again, based on what you're seeing in the first plot, you don't expect any relationship overall, while this plot is going to show you if there is equal spread across all of these values. The one here is similar-ish, but it is going to now show you after standardizing. So you're controlling for the overall variance that you have, whether this is overall a flat line or not. So the first plot and the third plot are very similar-ish. The third one is capturing a very specific value, which is it's trying to look at the standardized version of this residual. So I've removed the overall shift or the overall effect which is coming because of variance in these residuals. That's why the scale is much more squished here. It should be a flat line again, much flatter than what you're seeing here, for example. The fourth one is it has a constant variance, exactly. No, so this is, you can use this as a test for heteroscedasticity, because if it is at this point, if you start to see higher values here, this is after standardizing, that standardization is coming from their estimates. You'll see much more patterns emerge here. I'll do an example and become clear in just a bit. You will see most of your data should lie along this 45-degree line. Mm-hmm. Mm-hmm. Oh, I see. So this overall, like this is something. This is no. So this is continuous in some sense, actually. Like what you're plotting is it's percentile, right? Like it's written as quantile, but it's actually a percentile. So it's a continuous range, not like 10, 20, 30, 40, or 1, 2, 3, 4. It's actually a continuous value. That's why you see there's no jittering as such. Okay. Okay. So we'll see some of these examples, and one of the best ways to see those examples is to actually simulate the data and see what happens. If just to highlight what point I wanted to make over here, if there is lack of homoscedasticity, which means if this assumption breaks, it will be harder to see in here, because at this point you have not controlled for the overall variance, whereas in this case you have squished them. And if there is indeed flying off, or there is variation where the sigma is a function of, if it is indeed a function of x, at this point, if the range is not constrained, you can see some hovering around to happen. But the moment you standardize them, because you're estimating this variance from all of these residuals, it will get squished, and it will be easy to sort of see lack of homoscedasticity. So that is the important distinction between plot number 3 and plot number 1. Finally, you want to look for, are there points which have high leverage in your data, which means that including them will lead to the slope changing a lot. These are called high leverage points. We'll see what they are in just a bit, but overall they should not, you should again see a very similar flattish line. It will again not be very flat. What it is trying to show you is, if there is high leverage, that point can skew your slope a lot. These are likely outliers. They have high leverage, and because of this point having high leverage, your overall impact on the slopes that you're going to infer is going to get affected because of those, right? So ideally, once you standardize them, most of the data should lie here in -2 to 2, because again, these are supposed to be normally distributed. There should not be a lot of points hovering away from this, right? Because that would mean that because you have a very high outlier point, you're not able to, that is the one which is maximizing the residual that you get. So again, just to, before we see this actually in plots, if I have a lot of my points here, the line ideally should have just passed from here, assuming these points did not exist. But just because these points exist, it will be forced to pass through here, because I would like to minimize these residuals as well. Now the problem, however, here is that even though when I try to do it, my residuals, most residuals will indeed still come from here. because there are very few points which are outliers. So the line is not fully going to bend towards them, which means that they will have very high residual. I ideally want to remove those points from my analysis, right? Like these are your clear outlier points. We'll see how that is done in just a minute. In the, this is square root of the version, right? So the inside is positive, right? So you're only taking, in this case, you're only taking the magnitude of that residual, because you're interested in, once you have standardized, you're just looking at, is that spread very different from extreme values, which is 0 to 2, right? So it's going, is it going too far apart from it overall? No, no. If the, no residual, no. So residual will follow a normal distribution, right? So this, in third plot, essentially what you're doing is you're looking at just this extreme half of the values, because the other half is symmetric. This allows you to see things, the pattern emerges much more properly. Sure. Okay. Okay, fair enough, right? Okay, fair enough, right? So overall, yes, in once you do this, yes, you do expect most of the information to come about 0. Let's plot an example and see what is going on in that particular plot, right? So that point is correct, that most points should have come from 0. That point is correct. Let's see what is going on. Okay, any other questions? I'll do an example and become clear what is happening. Okay, so before we do that, just very quick examples to see some good and some bad fits. The one on the left is, of course, a good fit. Residuals are normally distributed. You can see that from the histograms as well. There is not much pattern between residuals and fitted values. They look almost flattish. Whereas if you do it in this case, this plot seems to be a non-linear relationship. If you force a line, you will be able to fit it. But if you plot the residuals, you will see a pattern, which is very clear from why that pattern emerges. You'll also see that this is skewed towards left. And of course, this bend is also showing you that they are not normally distributed. Okay, so we'll do the example. But before we do that, the last plot that I showed was to talk about how is leverage calculated. Very quickly, this is one way to calculate leverage. What is leverage is, you can think about regression in a setting that if a point is not extremely influential, even if I remove it and I repeat my regression, ideally I should get a very similar-ish line. But points like this, which are very far away from 0, which are very far away from the rest of the structure, they, if I remove, will have, if for example, if I get rid of all of these, the line need not bend anymore. It will possibly pass through this point. And this slope, which is, let's say, beta 2, and this slope, which is beta 1, has changed a lot in some sense, right? Ideally, you want to avoid taking that into account. This is one such metric that you can calculate to figure out, for at each point level, what is its influence. What is it doing essentially is it's deleting the jth point, the ith point from it, and repeating the entire regression, predicting what will be your yi, and how different is it if I were to keep that ith point included. So if you keep the ith point included versus you delete it and you run the model again, what difference overall do you get for all the endpoints that you have if you delete them one by one? That is what your metric of overall calculation is. So yji is the fitted y value when the ith observation has been deleted. Yj hat is just your normal predicted value for the jth point there. What is the overall difference divided by the overall variance? That is a measure of Cook's distance or leverage. This is for each point you can calculate how much leverage does it have. If deleting it does not lead to a lot of massive change, the leverage is going to be small. If it does, this value is going to be higher, and that means it's a higher leverage point. Okay. Yeah, the rank of the model in this case is just the number of overall non-zero coefficients that you have, which is just the linear algebra version of X transpose X, right? So what is the rank of that matrix? That's what it is. So this is constant, so it doesn't matter for all of it because you're going to just use these relative values to compare, but that's the actual calculation. Okay. Any other questions? Okay, so let's do a very quick example. So in the first version, what I'm doing is I'm simulating a normal. Let me set my seed. In the first version, I'm going to run a simulation with n 100 points of a normally distributed random variable, where y is a fixed function. I already know the function, which is 2 plus 3x. And then I'm adding some random noise, right? That random noise has a similar standard deviation. This is your epsilon, basically. This is a fixed relationship, 2 plus 3x, and this is the epsilon that you're adding. In this case, you know the full model, right? Like you know what is my y, you know what is your x. You should be able to fit a linear fit. Okay? So I'll do that, and once I do, I can always figure out how good is my model. So I had fit a model with slope is with intercept as 2 and slope as 3. You get slope as intercept as 2.4 and slope to be 2.9, which is very close to what you had estimated. Both of them are significant. Now, sorry. Now I can plot what does it look like overall. So there's no relationship between the residuals and the fitted values. The quantiles look almost perpendicular, almost at 45-degree. We do have a lot more stuff now close to 0. It's not always that it appears to be, while it appears to be at 1. Um, Also, this is actually, okay, 1 second, yeah. So just one second. Okay, so when we moved when we took the square root of these things here, what essentially I'm saying now is I'm going to take the standardize of taking the square root of this particular z value here. The fact that I did that, I am going to truncate it essentially, right? So all of the stuff which is over here essentially is going to just, you're going to just focus on this pattern here, and this pattern is slightly away. I still actually have to, not sure why the line is at 1, but I'm going to check and get back to you, right? Because it seems it's you're right, it does seem that the uh, value is more close to 1 and not to 0. And yeah, that's what, right, exactly, that they're more distributed towards 1 and not actually towards 0, right? That's what you're saying. Correct, which is easy because it's symmetric. In this case, what you did is you're taking exactly the same values, you're standardizing them, and then you're plotting it. You see that here also, which is that there's a lot more stuff at 0, which should have actually just remained 0. But in this case, you do see things changing. So let me see. This is coming from default R. So let's see if we can extract R. Okay, so these are my residuals. I will do scale So this is your hist of z dot scaled. Okay. Hmm. Clues. What is going on? Does it make sense? What is happening? No. Okay. Okay. Let me enhance it. Okay. So what I did is very simple. It's a interesting exercise. I extracted the residuals. I am going to scale it. So let's, yeah. So one second. Let me show everything step by step. So this is the histogram of Z, right? Let me reduce this further. Yeah. This is normal. Okay. Now I'm going to scale it. Okay. So let me do Z. So let me show you first this. Minimum value is -5, mean is 0, and third quartile is this. You can do STD uh, 1.82. I will now calculate the scaled version. So I do Z dot scaled, right? Your minimum is -2.5, mean is again 0. I will also do this. So this is scaled, which means this is my standard normal, which it does look like. Now I am going to do z dot scale dot sqrt. So I'm doing sqrt of abs z dot scale, and then it doesn't have the same property. Yeah, let me show you the previous histogram. Yeah, sure. What happened? Okay. Yeah. Yes. Exactly. Right. Does that make sense? So essentially, what happened was, let's plot this as well. Correct. So let me plot this actually, right? So let me also plot. Thank you for asking that question. Um, okay. So this is at if it is producing nans, which is negative values, there is nothing that it will show up, right? Now, if I produce, if I do a hist over there, then of the square roots, then you see the peaks coming at 0.5, right? Now, do you think what is going to happen next? If you fold, if you take the absolute value before doing it, yeah, okay, yeah. I'm just showing you 1 second. So here, essentially, what is happening is when you actually sum the effective second half from here, this is no longer the mode of your distribution. That mode becomes 1. I know, I know. That is what is counterintuitive. But does this make sense? First of all, we'll come to how it is happening. But does this make sense? What is happening? Right. So here, once you took the absolute values of let's do this. Sorry for the tangent, but it's a good question. So how should I diagnose this? Like, what is happening? How should I diagnose? Let's look at a table. Hmm? Okay, let's print the values. Let me do this. Let me do hist x is z dot scaled, and let me do bins breaks n. I want to do it in 10 classes, so okay, so so this, for example, now is what you see for your histogram. And we are not just plotting it, but its density is maximized at 0.95, which happens to be, or symmetric around 0.95, which is close enough to 0.7ish, right? Or similar-ish at 1 as well. We can do the same thing here. I am now going to just do for z dot scale. Its frequency is maximized at 0.44, which happens to be 0.0. This is something which we already know. 0 is the maximum. Now, when we take the square root of a positive of the absolute value of the random number, it follows a non-Gaussian distribution with a higher with a mode that has changed. So I need to think about this a bit. Say that again. Okay, good question. And I'm very curious right now. So are going to okay, folded normal. That looks kind of what we would expect. This is the solution. Um, okay, that's super counterintuitive. Yeah, yeah, sure, sure. This is what we got, by the way, right? Which is our empirical distribution is getting higher, close to 1, right? Like close to 0.95. It's super, super counterintuitive. There is a proof. Yeah, that's the key. That's how it estimates. So the counterintuitive part is that when we are actually thinking about this distribution, at this point, it's a standard normal distribution. The moment we took square root, that density function. So what is, so let's think about it. You can read the proof, but intuitively, I think what is happening is when you take the square root, for that entire area to become 1, having a peak at 0 is no longer sufficient. You need a peak at slightly other position for that entire area to become 1. Because that's the definition of your PDF, right? This is a new random variable, right? Square root of x is a new random variable. it gets scaled up. It has to get scaled up at some point. So that intuition, very, very good question. You get one bonus point, absolute bonus point for this. Which is, yeah. Hmm. 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 Correct. So the confusion, just to add, just to massage it, the confusion was that the density is higher actually at zero, right? The normal distribution. Sorry for this tangent, but I think it. Yeah, I like these tangents because they teach you something. So at zero, we had a lot of frequency, a lot of mass. When we took the square root of the absolute values overall, the assumption was that if initially we were getting a lot of frequency from zero, that should hold up in when you took the square root as well. The reason, however, it doesn't is because the distribution properties, when you take the square root, the amount of changes that it can see is lesser, right? Like the amount, the sample space has in some ways slightly shrunken, right? And because of this, the mass that you were initially seeing at zero no longer holds, right? So that frequency which you should have otherwise seen to be high at zero no longer holds, and that's why you get that plot at one, right? So very, very good question. Does that make intuitive sense? We'll not do the formal, know the link to the thing, so you can always go back and see what the formal proof is. But it's a very interesting question. I will share the link. There are actually a couple of lot of links pending from my side, so including the thing that I promised. So I'm going to share all of them at once. These are all for you to play around with. You know, like as you've seen this, the kind of quiz that you gave, you can expect similar questions for the exam. Thought questions. Think. Maybe there'll be some more calculations, but mostly thought. And if any formula is required, I will give it to you. Okay. Okay. Back to the lecture. So let me, rather than showing you slides, let me just show you different scenarios now that we have slightly better understanding of what is happening. So the first thing that we did was a good fit. We can now think about that if we started with a non-linear model, right? So if we started from x2 here, which is uniformly sampled along the x-axis, but y2 is a new random variable which follows a squared relationship. So this is y plus 3x plus 2x squared. I'm going to now fit a linear model here because I can. And if I now show you, sorry, one second. Hold on. It's because it doesn't like the amount of zoom that I have. So in this case, of course, I started with a nonlinear model. So the relationship was not normal, and that's what you see in the case of residuals as well. It starts to break all those assumptions. And now you can also see what is happening in this case. Overall, because you had a nonlinear relationship to begin with, the first plot tells you about overall what is the relationship, because this is same scale as the original data. This tells you that there is some information that is weird in terms of how the residuals are distributed. Because of the fact that this is a it's a non-linear relationship, you'll get two kind of relationships. You will get two kind of overall residuals. One which are going to be very close to this line, and those are sort of the good ones, and the ones which are away where the line starts to deviate a lot, and those are the two things that you can see here in this particular. You can also see that there are the residual, the leverage is higher again because of these points. These points are pulling your line towards them, but it cannot. So that's why overall, there, as the value of the leverage increases, your residuals are suffering. They are resulting in larger residuals overall. Okay, one more example, which is, so far we have been assuming that when I add this noise, so here also when I added the residuals, right, these are the this is the, sorry, two more examples. When I add the noise at every point, this is a normal noise, this is standard normal, or this is normal with a standard deviation of 3. I can inject an extra variance term here, right? So here I'm again going to simulate X, but when I generate the, yeah, when I, so this is my X3, which is just a random number between, I'm generating 10 random, n number of random numbers with a standard deviation of 10. Sorry, this is uniform between 0 and 10. I'm generating n number of uniform numbers between 0 and 10. And when I calculate y3, the variation that I'm adding, earlier I was adding a fixed variance, which was 3 or 2 or 1. In this case, this variation is changing with x. Okay, so let's look at what does this tell us. So this model is no longer homoscedastic, right? So you can see that while this looks okayish, right, like overall it looks flattish, you cannot make out the pattern, but when you actually see the standardized versions, you can see that there is a shift of the of the homoscedasticity, because this line which should have been flat around here is now taking a trend, which means your variance is not constant. And in this case, I know because I was the one who added that variance. And finally, you have the point about outliers. So here y is 2 plus 3x, but now I'm adding extreme outliers here at towards the end. Everything should have a mean of the x's in this case should had a mean of 5 and standard deviation of 2, but I'm adding values like 10, 12 and 8, which are very, very different from a normally distributed random variable with a mean of 5. So let's look at what that looks like. So this is an interesting plot. Overall, the residuals were okayish, but there are so many outliers, the 3-4 outliers that I added, that overall the residual now is extremely large for them. And you see this again and again in this pattern as well, but particularly very clearly in the leverage plot, that those 3 points which I added are totally standing out from your entire distribution. Okay. It's done by R itself, right? So it identifies that these are the contours at which you, which is deviating from a standard specific threshold. These are all automatically numbered by R, like which points are outliers. Okay, any questions? Sorry, that took a bit longer than I had anticipated, but I guess hopefully all of us have learned something new. Okay, so we're going to change the problem a bit, and we're going to talk about a new problem where somebody is interested in understanding how does systolic blood pressure or your hypertension or the blood pressure that you have, what is the relationship between this blood pressure levels of newborns and their birth weight, right, or their subsequent adult blood pressure. So you measure the blood pressure of a newborn, and then you want to see that today when the baby is born, their blood pressure is X. What would it be in their adult life? If you can measure it and you can predict, that's great, right? You can predict whether that baby is going to have hypertension to begin with or in the future. The problem, however, is ideally this is the prediction problem that you would like to work on. The problem, however, is that the blood pressure itself is a function of the birth weight of the baby, right? So before we do any modeling, we would like to understand the relationship between how does the blood pressure that you measure for a baby when they're born, how does it vary across different birth weights and the age of the baby when this is measured, right? So Of course, as the baby is aging, you will have changes overall. You're interested in capturing this relationship, right? You're eventually capturing how does the age influence your blood pressure. This is what you're trying to capture. But it also varies as a function of the birth weight, and that's something which you would like to adjust for, right? So how would you attack this problem? How would you solve this problem? One Oz is 400-ish grams or 250 grams. This is taken from your textbook, that's why it's Oz. 400 grams, right? You know how much? No, so these are different babies, right? So these are overall. It can vary based on uh, which baby is born where. I is the ith number of observation. So this is ith individual subject. How would you plot this or solve this relationship? So the simplest method here that you can try to fit is what's called multiple linear regression model, right? So I'm interested in SBP, which is your systolic blood pressure. The first model that you can fit is this. How does the blood pressure vary as a function of age? I can also fit a separate model, which is how does it vary as a function of birth weight. If I do this, this is simple linear regression, one outcome, one predictor. But if I want to jointly see how does it vary as a function of uh, both of these variables, I do what's called multiple linear regression, right? So the entire idea of multiple linear regression is very, very similar. We make similar model beta 0 plus beta 1 x1, but now there are p predictors, p values. We can make predictions once we fit these coefficients. You determine these coefficients again by minimizing the residual sum of squares. If you know what your yi is, you know what your beta naught overall value is. Again, we'll use minimizing the same concepts that we had used previously. We will not derive them, but that's something which the idea is very, very similar as to how you derive these coefficients. There is, however, a one important distinction between how do you interpret these coefficients. So when I fit a model like SBP is a function of age, right? Let's say this is beta 1 and let's say this is beta 2. What is the interpretation of beta 1? What does it tell you? What is beta 1 trying to capture? If you were to explain this, for example, to a doctor who would like to use this to understand that today if they have an age maybe 3 days and tomorrow they get an age maybe of 4 days, how is that beta 1 important for them? Like, what does it tell anyone? What does it tell that what is the interpretation of beta 1? Okay, so beta 1 is, yeah, finish change per unit change. You said all the key terms, but you have to put them together. Very good, right? So for 1 unit change in x, there is one term missing. On average, right? So if x changes by 1 unit, then the beta 1 is the amount of change on average that you would see in your blood pressure, right? The average is important because you will know that what you said is right, which is that there will always be an error, and that's why on an average, because those residuals will get 0, that on average is important. On average, if the age changes by 1 day, beta 1 is the amount of change in blood pressure on average. If the change, for example, in age, if I measured it in days, that is what it will capture. Same thing for beta 2, but when I put them together, beta 1 plus beta 2. What is the interpretation then? So multiple linear regression. Yeah, let me put it down now. So what is the interpretation of beta 1 now? This is the what that was your question, right? Okay. What is beta 1? Rate of change. Okay. What is rate of change? Huh. With respect to age. Okay. Anyone else? You have two coefficients now. Wonderful, right? Very, very good. So beta 1 is the on average change that you will see in your Y, which is your systolic blood pressure, assuming everything else is kept constant, right? That's the important part. If A changes by 1 day, everything else at this point is constant, then Y will change by this amount. That's what the interpretation of beta 1 is. Similarly, for beta 2, if you are trying to interpret beta 2, then you will have to talk about this part being constant. Like the age cannot change. It is the amount of change that you see in your systolic blood pressure if that changes. So let's say your beta 1 is 5 and your beta 2 is 10. Is can I say that beta 2 is more important than beta 1? Or birth weight carries more importance because it has higher weight? Is that something which I can conclude from betas? So just to give you some preview of the slope is a measure of correlation, right? This is what? It's nothing but the amount of covariance that you see in your data and having accounted for the variation that you see on the X, right? So how much can I determine Y? That is my beta 1 in the simple linear regression setting. Higher beta 1 is, I'm able to predict X or Y better. That's what it tells you overall. So if this is what you're seeing now with multiple linear regression setting, what can I conclude? Is beta 2 more, is BWT more, birth weight more important than age? Okay. So elaborate. Mm-hmm. So let's say you have it in control. Let's say you can control this thing, right? Like age, maybe swap age for, let's say, uh, nutrition, and swap birth weight to be amount of proteins they had or something, which is education. For example. Fine, education. But would you say that beta 2, if it is higher now, then that carries more weight? Okay. Anyone else? You have all seen this, right? It's nothing new. Let me. Hmm? Yeah. Okay. Okay. So let's do that example really quick, right? So the first thing that I'm going to do is let's just plot this, right? This is your age as to how your blood pressure is changing, and this is birth weight and how your blood pressure is changing, right? X-axis changes, y-axis is the measured variable, so that doesn't change, that remains constant. This is the pattern. How will you assign importance? Like, I do regression, and let me show you the regression as well. Let me do a simple linear regression first on age, and I get coefficient as 6.1 for age. I do for birth weight, I get 0.15. Okay. If I just take age, I get 6.6. If I only do birth weight, I get 0.15. Okay, let's do both. Age 5.88, birth weight 0.12. All of them are significant, luckily. What does it tell me about the model? Or what does it tell me about what have I learned actually in the process? Can I conclude anything from here? For 1 unit change in age, keeping everything else constant, blood pressure goes up by 5.88. For 1 unit change in birth weight, it goes up by only 0.12. So assuming those units are kept as it is, this seems to have more variation. But does that mean that that's more important? Okay, good. Okay. How will you normalize the data? Okay. Okay. So if you see here right now that everything that we are predicting is at different scale, right? Look at the scales here. Look at the scale of SBP and look at the scale of birth weight. They're kind of on a similarish scale, but age is very, very small. And if you're trying to predict y as a function of x, you'll have to, of course, multiply it with a larger factor. There is no denying the fact that you'll have to multiply this with a larger factor to get something which is 89. So if you don't normalize or if you don't account for the variation again that you see in your x and y variables, once you do a multiple linear regression, you cannot conclude anything. All you can conclude is whether these are significant or not. There's nothing much that you can conclude from the magnitude of the coefficients. It's not that this is high, so this should be more important. That conclusion is made up in a lot of papers. That's incorrect. That's not right. It's just a fact that it is trying to catch up to the scale that you have. So if they're not on the same scale, you cannot compare those coefficients. The only thing that you can compare is whether they are significant or not, and in this case, both of them are significant. So there are two ways to normalize. One is that you could normalize the data. The second is you can multiply these coefficients by, again, the variation that you see in your x variable and divide by the variation that you see in the y variable. The reason you're weighing this by x is if the variation in x is higher, then that should get accounted for in your final coefficient, right? So the standardized regression coefficient is given by beta sx by beta y or by sy, so that everything now is on the same scale, which allows you to interpret overall what is going on. This is with respect to per unit change in x. So you're multiplying this by the same scale value and then dividing it by sy. So now this quantity is comparable across x's and y. The second way to, of course, do this is to normalize your data. So I can bring this to all to the same scale. So I'm going to again use the same trick. This is what my scale data looks like. So if I do mean data.scale, sorry, I'll have to define my data again. Sorry, I overwrote it. If I now do a mean or a variation on this, all of this will be 0. You can also check for variation. So I have essentially brought them onto the same scale. I've essentially standardized them. So mean is 0, variance is 1. That's going to be true for all the variables that I have. Now I can do a second round of fit. Yeah. So now I've normalized all of them, and you'll notice that the values of the overall estimates of the slopes have now reduced, right? So we had 15 in one case, or 12 in one case, and 0.15 in one case, or 5 and 1.15 in each case. Now all my data is on the same scale. So this is 0.08, this is 0.03, right? So for every 1 unit change in the standardized version of my age variable, I see a 0.08 change in systolic blood pressure. Now these are comparable because I brought them all under the standardized scale plot. I can say that irrespective of whatever I measure, everything is now on the same scale. So for every 1 unit change in age in the standardized version, I see a 0.08 change in systolic blood pressure, whereas that is 0.03 in the case of birth weight. So this has slightly more importance in terms of amount of change that you see. These are again both significant. The significance will not change if you scale these variables. The p-values have slightly different. This is same Sx by Sy, right? So this is just same Sx by Sy because now Sx and Sy are both 1. So this is the same thing. You now have brought them both to the same scale. Yes, exactly. Yeah, exactly. Okay, is that clear? So again, all of you have done this. So none of this hopefully is new, but this is just something that you should keep in mind, that this is how you interpret these coefficients. Okay, so I've already shown you all of this, so I can quickly skip. And once you've done a linear regression, there are 4 main questions that you can ask. That is, at least one of these predictors useful in predicting the relationship between y and x? We have p predictors now, right? Like we have multiple predictors. We can fit, of course, but the question that we have to ask is at least one of these useful or statistically significant? The second question that you're going to ask is, okay, how good is the model fit overall? The third question is, do I really need all the variables? Do I need to keep some of them? Should I keep all the p of them, all 100 variables if I have? Should I keep all 100 of them, or should I do some sort of selection? And finally, once I make the choice that of the 100 I only want to keep 50, then how should I actually do the prediction? Okay, so we will only take the first part here because it's something which I can teach you in 5 minutes. The problem again of multiple linear regression is actually of hypothesis testing, which is the hypothesis which, if you remember, or if you recall, in the case of simple linear regression was beta 1 is 0. Now you have p variables. The hypothesis has now changed to, is beta 0 equal to beta 1, is beta 1 equal to beta 2, equal to all the way equal to beta p is equal to 0. So the coefficients of all the p covariates that you have in your data is 0. And the alternate is a very simple one, that at least one beta j is non-zero. How do you test this, right? We test this using what's called F statistic. The F distribution, I'm assuming, has not been taught, right? F distribution has not been taught, right? We'll see this very, very quickly. It's a very simple distribution. These two proofs we are not going to do, but if the linear relationship is indeed true, the expectation of the residual sum of squares divided by n minus p minus 1. P, if you recall, is the number of covariates. If this is linear regression, simple linear regression, P is 1. If not, then P can be anything, which is the number of covariates that you have. Its expected value is sigma square. And if the null hypothesis is true, then the expectation of TSS minus RSS divided by P is also sigma square. You'll remember this quantity here, and it will make sense in the next slide why this is a quantity. If both of these hypotheses indeed happen to be true, which means that linear relationship is true, and if the null hypothesis is true, this becomes sigma square by sigma square, and the value of F becomes 1. Which means that if the value is 1, then there is no, then you cannot reject the null, which means the null in this case is beta 1 up to beta p is equal to 0. Okay, and the linear relationship, of course, is assumed to be true if this happens to be 1. So if you want significance, if you want things to be different, if you want your linear relationship to hold, you're looking for F statistic to be high statistic. So you can reject this null. This usually is going to hold up, but this is what you're trying to reject overall. Okay, is that clear? Okay, right. So what is the F distribution? This came from a statistician, American statistician, Senecdor. I still don't know how to pronounce it. He devised this is F distribution. It's very, very simple. If you have two chi-squared values, if you have two chi-squared random variables, if you take a ratio of them divided by their degrees of freedom, then it follows an F distribution. You can see that this is a very skewed distribution. It's not symmetric unless you really stretch it out and make the degrees very, very high. Overall, with very small degrees of freedom, or even with slightly larger degrees of freedom, it's going to be a very skewed distribution. Okay, so this is usually employed to test for ratio of variances. If you think about model fitting and if you think about multiple linear regression, all you're caring about is, once I fit a model, am I able to explain the variation that I see in data, right? When I see a plot like this, there is variation in Y. You're trying to come up with an explanation of that variation, and this model is supposed to help you do the job. So variation is coming because Y values are different. I want to explain it, so I fit a model, and if it is a good model, it will be able to explain all the variation that is there in your data, right? So you saw the terms TSS, RSS, and so on. TSS is the total sum of squares, which is the amount of variation that you see. A good model will try to capture all the variation. So your residual sum of squares should be 0, or TSS minus RSS should be equal to TSS, right? RSS is residual sum of squares. Any idea why this is called the F? What is F about it? Why is it F? I don't see an F anywhere. Why is it called an F distribution? Every other distribution you've seen, you know why it's called that, right? Gaussian, because Gauss had used, huh? It fades quickly. Okay, that's an interesting hypothesis. There are other distributions also which fade quickly, right? Normal is called normal because, there's a, again, Gauss discovered it, and then the normality sort of term was used, so that became normal distribution. Poisson, because Poisson was a scientist who discovered that. But what is so chi and t? Good question. So chi is something which came from the Greek version. I don't know the origin story of chi-square. I'm going to go and look it up. T distribution, right? Actually, I used to remember the story. I have forgotten why it's called T. No, no, that is. Oh, sorry. Yes, of course. I forgot. How can I forget? Yes, student T distribution. Yes, the reason it's called T is because um, this person, what was his name? Forgetting the name. I shouldn't forget the name. Let me recall. So he was employed anyway. I'll tell you the story. He was employed in a brewery, which is this what is that? Guinness, right? So Guinness was a brewery where he was employed, and he was not allowed to publish papers because it's a brewery. You're competing with other breweries. This brewery has got a new grain, which it's going to test whether it gives you better yield. And he devised the tea. He called it the student's tea because he didn't want to give out his name there, and that how why did it call it tea, that is still not clear, or at least that I cannot recall. But he published it with this name called student's tea distribution. So that's why it became the tea distribution that way. Chi-square has some Greek story. F is the story that I'm looking for. Anyone and recall that you recall in this class a test that starts with F? Yes. So it's named after Fisher. Fisher was, among many things, he was a statistician at some point, but he did other things also, some good, some bad. But this distribution is named after Fisher, Ronald Fisher. Okay, so we're out of time. We'll come back. We're almost done actually. But what we are planning to see now is if you have done this test, if you have done multiple linear regression, how do you assess whether each coefficient is important or not? So the simpler idea there that I can go back and look at all the p-values that I get and choose, okay, this is significant, I'm going to keep it. But is that the right approach, or can you do a better test to test whether which coefficients you should keep, if at all? We come back on Tuesday, we'll do this exercise. Your assignment is due soon, so if you have not started to work on it, please do. I might have a very small, another very small assignment, just which will cover linear regression. That will be due after your end sems, but you will get it before your end sems.